Okay, so this is day one of the tablet era. It's going to be a great time for all of us. Yeah, right, exactly. Today is 0 TE. All right, well, so here's the idea with deform. And I talked about this a little bit in statics when we started doing internal loads. Okay, so what's the deal with deform? Really what we're trying to do is we're trying to predict damage or failure of materials. That's what all this is based on. Let's say in engineering applications. And external loads don't tell the whole story. Let's say they don't explain that. And to me, the clearest example is okay, so that's one hand. I don't know what's wrong with your thumb. That thumb's better. It's going to take me a while to get used to drawing on this thing. Okay, so say you're holding a stick between two hands like this. Free body diagram of the stick looks like, well, there's a force here and a force here. Force here and a force here. Okay. So those are the external loads, but that's not where this stick would break. The stick isn't going to break at the location of those external loads. So there must be something else going on that we need to get to. And from statics, you know that the answer is the internal loads, right? Or at least that's the next step in getting closer to this. Did I say external? Internal. Okay, good. So we calculate the internal loads. But imagine that stick is, instead of being solid, imagine that it's hollow with a wall thickness like this. Okay, so say that this is the wall, this is the hollow part. Okay. Well, if you calculated that the internal loads were greatest here, okay, based on internal loads, you might expect damage or fracture to happen here. But because of the shape of the wall thickness, because that's where it's reinforced the most, you're actually not very likely to have anything happen there, you know. And so we need so So let me write that, I guess. So even if the internal loads are the greatest at the center, the geometry might prevent damage at the center. So internal loads aren't enough on their own. And so we need to go another layer deeper into this, and we end up with the concept that this class is based on. So the next step is stress and the related idea of strain. Stress is a measure of load, and strain is a measure of deformation. And stress and strain are both properties at a material point. Okay, so the idea of this deform is really just an introduction to stress and strain. So let me give you sort of a layout of kind of how deform fits into mechanics. Okay, so over here to the right is circuits and whatever. But over here in mechanics, we start out with statics, and then from there we kind of branch into two directions. Over here is deform, over here is dynamics. This side of things is all about predicting damage. This side of things is all about predicting motion. So you apply loads to things. Two things can happen, and they can both happen. You know, the material can absorb some of the energy that you're putting into it, and that creates damage, or that energy can be turned into kinetic energy, and that produces motion. You know, and these are kind of the two sides. Dynamics. After that, you go into fluid dynamics, or more advanced solid dynamics. And if you major in aerospace or mechanical engineering or civil engineering, you're going to take, you know, more advanced dynamics, and you're going to take fluid dynamics. And then from deform, you can sort of go in two directions. Well, probably you're going to have to go a little bit in both of these two directions. One is continuum mechanics. that's a very mathematical area where more advanced deform type problems are solved in a closed form by solving really complicated partial differential equations. And then the other more practical direction you can go from deform is finite element analysis. This is a numerical approach to solving complicated deform type problems, figuring out when things are going to fracture. Okay, so you are here. Yeah. This one, finite elements. So, like if you're working for a company or working on an academic project and you need to get accurate predictions of what a real application, like the likelihood of fracture at a certain point on a real application, what's the likelihood that you'll do it with continuum mechanics versus what's the likelihood that you'll do it with finite elements, percentage-wise? 100% finite elements, 0% continuum mechanics. Okay, this is like a branch of math, kind of, you know. So this is how you solve these problems for any practical application. Okay, you use a finite element software package, and you use this complicated, basically differential equation, numerical differential equation package to solve these problems for you. What we're going to be able to do are very simple problems, not, you know, in some sense, like they really won't be applicable to anything that you ever really, like in any real world setting. None of the calculations we're going to do are going to directly apply. So this is sort of what I want to, let's see. If all practical applications use finite element analysis, FEA. Okay, so that's finite element analysis. Why do you take deform? Like, what are the goals in deform? And I would say there are really two reasons that you take deform. The first one is in order to interpret finite element, let's see, to interpret finite element results, requires an understanding of the meaning of stress and strain, and we'll see that they're actually sort of complicated things, making sense out of them. And the second reason that you need to know something about deform is because it'll give you a way to sanity check your finite element results. So, for example, we're only going to be able in this class to do calculations for very simple geometries. You know, like let's say, for example, like a hollow circular tube or something. Okay, so in a real application, you might have a tube that has a varying cross section or whatever. It might be circular at some point, whatever. But at least we can use our techniques to come up with an approximation with a geometry that's close enough to the real geometry that we can do a hand calculation and make sure we're not making some mistake in our finite element model. You know what I mean? So those are really the two outcomes that we want from this class. The results that we're going to come up with in this class depend on 4 main simplifying assumptions. So maybe all is a little strong, but that's supposed to say almost. Oh, this is where the yeah. For some reason it's harder at the edges. Okay. Almost all of our calculations will depend on 4 simplifying assumptions. The first one is that the deformations that the materials go through are small. In most of the engineering materials that we're worried about, the percentage of deformation is going to be on the order of a 1/100th of 1% of the total length. Okay, that's the biggest that it's going to be. Like if you imagine like a steel bar in an engineering application, okay, and you put a big force on it and you're trying to see how likely it is that this steel bar is going to break. You know, you can apply a pretty big force to a steel bar before it deforms 1/10 of a percent. You know what I mean? It's not stretching very much or contracting very much. So let's say, just as a general rule, God damn it. Come on. Oh, I was pressing the wrong button. Okay, so less than about 0.01%. Okay. Second, we're dealing with materials and applications with those materials where the relationship between stress and strain is linear. So linear relationship between stress and strain. Can you think of a mechanical relationship you've seen? There's one, I think there's only one that you've dealt with so far, where the relationship between the load and the deformation is linear? Spring. Yep. And so we're going to deal with it in more than one dimension, but this is going to be a 3-dimensional version of Hooke's law. Okay. Obviously, like for a steel bar, the constant of proportionality is a lot bigger than for a spring, but the idea is the same. Third, all the materials we're going to deal with are homogeneous, which means as you move from one point to another, it's the same material. We're not going to have steel bars with sections of wood inside or whatever. You know, we're not going to be dealing with reinforced concrete or whatever. So homogeneous materials. And if you do have cases where you have more than one type of material, you have to deal with the two different materials separately and deal with what's happening at the boundary between the two of them. So homogeneous materials means same material at every point. And the last one, so homogeneous means you can go to different points and the mechanical behavior is going to be the same. The last one is that the materials have to be isotropic. And what that means is the material behavior is the same in any direction. So things like, well, wood, things with any kind of preferred grain direction, you know, you have a stronger material with a bigger constant of proportionality in one direction than you do in another direction. You know, the behavior is different depending on whether you're loading with the grain or loading against the grain. Okay, there's a lot of materials like that, but for the most part, engineering materials are not that way. Steel, you know, no matter what direction you try to stretch it, the constant of proportionality between deformation and loading is the same. Okay. So anything with a grain direction is not this way, is not isotropic. All right, so let's think a little bit about where all of these come from, sort of. Which of these come from the material itself, and which of them come from the loading environment that the material's in? Okay, so small material deformations. Okay, the load. Yeah, right. I mean, in a way, it's kind of both of them. You know, if you apply 10,000 newtons to a blob of silly putty, it deforms a lot. If you apply 10,000 newtons to a big chunk of steel, it doesn't deform very much. So this one, let's say this depends on the material and the loading environment. What about a linear relationship between stress and strain? That one actually, it depends on both again. A lot of materials, especially, luckily, all engineering materials have a range of loads where they will be pretty much linear. And if you exceed that, then it'll become nonlinear. There are some materials that are never well approximated as a linear relationship between loading and deformation, like rubber. If you stretched out made a strip of rubber and stretched it out and measured the loads and measured the deformations, it would be rounded the whole way. You'd never find a region where you could fit a good line to it. But with engineering materials, there's a region where you could fit a pretty good line to it. So again, this one depends on both the loading environment and the material. Homogeneous materials. Yeah, that's a material kind of either is homogeneous or isn't. Yeah. And then what about isotropic? Yeah, that's material too. In the rare instances where we don't make these assumptions in this class, I'll try to point that out. I better put this try in here just for legal reasons. So there's a couple cases where we'll talk more generally, but basically all the mathematical techniques we're using depend on these four things. Anybody have any questions about any of that? All right, so before we go on to doing deform calculations and defining the stress tensor and defining the strain, I want to do some mathematical preliminary stuff. And what we really need for this class is being comfortable with matrices. Okay, everything is going to be matrix math. And so I'm going to talk about how to do these calculations, and I'm going to tell you how to do them on your calculators. Okay, so let's say that we have a matrix. So we have this matrix A, and the same way you represent vectors with an arrow over the top, most people represent matrices with a little undersquiggle. So let's say our example matrix is 2, 1, negative 2, 4, 0, 6. This is called a 3 by 2 matrix, where the first number always gives you the number of rows, and the second number always gives you the number of columns. And if you want to talk about the individual elements of the matrix, so usually people write the names of matrices with an uppercase letter, the elements of a matrix with lowercase letters, and then you give the row number followed by the column number to indicate the element. So A11 is 2. A12 is 1. A21 is -2, A22 is 4, A31 is 0, and A32 is 6. And just like if you're writing a, if you're writing a vector, you have a vector v, you put the arrow over it, and that vector can be broken up into components. And you don't use the vector symbol for the components. Those are just numbers, right? It's the same thing with a matrix. So you don't use the undersquiggle for the elements, just for the whole matrix. We are going to deal with primarily four sizes of matrix. The first one is, this is the one the class is kind of built around, a 3x3 matrix, and that's the size of the stress tensor. So the stress tensor is represented as a matrix. And so it'll, for example, it's represented with the Greek letter sigma, squiggle, and it's going to have big values, say like 5 times 10 to the 6 pascals, 0, negative 2.5 times 10 to the 7 pascals, 0, negative 1, where am I getting these numbers from? They're just totally random. 0, almost random except for one important thing. Okay, so there's a stress tensor in pascals. And there's a significance to the fact that we have zeros here and here. Well, it doesn't matter that there's zeros, but it matters that this element matches this element matches this element, and this one matches this element. Okay, I'll write this down later, but the stress tensor is always a symmetric matrix, which means if you interchange the row number and the column number, you get the same value. Okay, so sigma 3,1 is equal to sigma 1,3. For example. So I'm sort of trying to do these in order of importance in this class. The second most important one is a 3x1 matrix. And that's how we're going to represent vectors. Anyone who took statics with me, that's how I represented vectors in statics too. So, for example, a force vector would be like this. And that represents the x component, y component, and z component of a force vector. The third type has a size 6x1, and that is a second representation of the stress, and it's the only representation of the strain that we're going to use. That way of representing it is called the Voigt form. So the Voigt stress and the Voigt strain are both going to be, there's no H, are both going to be written this way. So for example, the strain could be negative 1.5 times 10 to the minus 6, 0, 6.0 times 10 to the minus 7, 0, 0, 5.5 times 10 to the minus 6. Okay, this would be an example of the Voigt strain. And one thing you can see from the two totally arbitrary examples I gave of the stress tensor and the Voigt strain is something that's just generally going to be true. We're going to be dealing with big loads and small deformations, right? Small deformations are actually required for, that was one of the 4 assumptions that we had to make. And so whenever we're talking about strain values, you're going to see little values. I haven't talked about what strain is yet, but you're going to see values much smaller than 1. When you talk about stress values, you're going to be talking about big values. Okay, our methods would work fine for stress values of 10 and whatever, but the thing is, we wouldn't even bother to calculate them if they weren't times 10 to the some big number. They wouldn't have any effect on the material that we're talking about. Okay, so that's your first clue to whether you got a problem right or wrong. If you ever do a calculation and you get a stress value that's less than 1 or a strain value that's bigger than 1, you probably used the inverse of the matrix you should have used for your calculation. Okay. And then the 4th type is 6 by 6. Oh. God, I did that yesterday too. So hard to write over here. 4. Okay. Is that right? Now, is it okay with you? Can I go on? Okay. So 6 by 6 matrix. And this represents the stiffness matrix and the compliance matrix. Those are inverses of each other. I'm not going to write that out because you can imagine a picture with 36 numbers in it. But the definition of this stiffness matrix is the stiffness matrix is a matrix that relates the stress to the strain and vice versa for the compliance matrix. So the Voigt strain is equal to the compliance matrix times the Voigt stress and the Voigt stress is equal to the stiffness matrix. I'm going to call that E times the Voigt strain. This is the stiffness matrix. And C, the relationship that they have to have based on this is that C is equal to the inverse of E, and E is equal to the inverse of C. Okay, we'll talk about what all that means. I don't know how much you've done of this kind of stuff. You don't want to do these kind of calculations by hand, especially like multiplying a 6 by 6 to a 6 by 1. It would take forever. But your calculators, TI calculators, do it instantly, you know. So how do you enter this stuff in a calculator is an important question. And all the TI calculators do it a little bit differently. If you can't get it working on yours, come talk to me. I think I know how to do it on all of them. If I don't, we can figure it out. There are two main ways. Some calculators, both of these work. Some, only one of them works. Okay, so let's say that our example matrix, let's say that it's the one we started with. So A is equal to 2, 1, negative 2, 4, 0, 6. Okay. The first way, square bracket, 2, comma 1, semicolon, negative 2, comma 4, semicolon, 0, comma 6, square bracket. That's the fastest way, so if that works in your calculator, that's probably the way you'll end up doing it. Then the other way is square bracket, and then another square bracket, set of square brackets representing each row. So 2, comma 1, close square, open square, negative 2, 4, close, open, 0, comma 6. Okay. Any questions about any of that yet? Okay, so now we have to talk about some different matrix operations and definitions. The first one is the transpose. So any matrix has a transpose defined by element A, I, J, let's see, how do I want to do this? No, erase that. Defined by putting the Ji element where the ij element used to be. So, for example, if A is equal to 1, 2, 3, 4, 5, 6, then A transpose is equal to, well, so this is A11. If you change the row and column around, you still get 1, 1, right? So this 1 goes here. This is 1, 2. change those, and you get that A21 is this. You follow what I'm doing? Sometimes, okay. Sometimes what I say, I can tell it's not that clear. This is one of those times. But it's not a very hard concept if you use the right words to describe it. Okay, so 3, that's A21, right? So this one, that 3 goes in A12 for this one. You are rotating it, and you're rotating it and sort of flipping it too. You're flipping the subscripts. That's all you're doing. Okay, so I was waiting for you to say it. Okay, so that's enough of that. That's the transpose. In every matrix, you can do the transpose that way. And the transpose is a really useful thing. The transpose is built into TI calculators. So if you go like 1, 2, 3, 4, 5, 6, and then use this button to store it in a variable. I think on your calculators that might be written as STO or something, but that's how you put stuff in variables. And then if you go to the catalog of functions, you can just go and press the button T. It'll take you right to that transpose thing. So enter the variable T, pop that transpose onto the end, and it'll spit out the transpose of that matrix. Okay. Ooh, we got to stop. Anybody have any questions about this so far? Or I guess particularly any questions about the 4 assumptions or kind of what this class is about?
Can you say that the transpose, how to do that? You just do A raised to T?
No, you can't do it like that. It's a function that you have to. So go to catalog, and you have to find that little t, and just. Yeah, I don't think all the calculators have that matrix function thing, but if it does, then yes, definitely that's a function in the matrix, in your matrix area. Okay.